Hello students, this is Dr. Faizan Mirza. In this video, I'll be covering with you the Hill's reaction and how the DCPIP actually loses its color, its blue color when exposed to light. And because of the light energy, as it loses its color, you can note down the time taken for the DCPIP to lose its color. And the contents of the tube will again become green because the chloroplast has been added there. If the chloroplast suspension was not added and if it was distilled water with the DCPIP, you know that the content would be blue. And if you expose them with this light, they would stay blue because the DCPIP would just not undergo the process of gaining hydrogens because just water cannot split in the absence of chloroplast. So just recall that kind of theory from your chapter of photosynthesis because this question deals with that. Why I have picked up this question? Number one, because it actually points out to a very important aspect of your photosynthesis chapter, in which we study DCPIP and the Hill reaction, how the loss of its color can be used as a variable to find out the rate of, you can say, light dependent reaction. This question came in May June 2018. This was the second variant of paper 5, and this is question 1. Another reason why I picked up this question is because in this question they asked you to calculate the small n value, and they provided you with the degrees of freedom. Now this is a different kind of question because so far every time they ask the t-test, they ask you to calculate the degree of freedom and n is provided. In this it was the reverse. N was not provided, degree of freedom was provided, and n was to be calculated. So let's come discuss this question first. So first of all, they have given you all the description regarding the theoretical concept that you need to recall. During the light-dependent stage of photosynthesis, hydrogen ions and electrons are released from photoactivation of chlorophyll and the photolysis of water. These are added to the carrier molecule NADP, changing it from the oxidized state to reduced state. We have studied this in photosynthesis. You should be very familiar with this reaction. DCPIP is a blue dye which becomes colorless when reduced by hydrogen ions and electrons. As shown, this is the Hill reaction that you must have studied in photosynthesis chapter as well. A student used DCPIP to determine if the reaction in the light-dependent stage had occurred in the suspension of chloroplast. The suspension of chloroplast were prepared by grinding, filtering, and centrifuging a sample of leaves with ice-cold extraction medium. Why ice-cold extraction medium? Because ice-cold extraction medium reduces the chances of the enzyme activation. So the enzymatic reaction will actually slow down at the low temperature. By grinding, by filtering, because of the cell walls are there, the cells will have to be crushed, the cell membranes have to be broken, so the chloroplast can come out. So that's the chloroplast suspension. Centrifuge to concentrate the sample and to just to take out the chloroplast suspension from the overall liquid. Four tubes covered in foil were set up containing the mixture in table 2.1 to table 1.1. So these are the contents of the four test tube. In one, you have chloroplast suspension and DCPIP. The second, chloroplast suspension and distilled water, DCPIP extension medium, and chloroplast suspension and DCPIP. We know DCPIP is blue in color. We know chloroplasts are green in color. And if it's DCPIP and extension medium together, it will be blue. If it's chloroplast suspension and DCPIP, it will again be blue. So all chloroplasts and DCPIP will be blue. Chloroplast and distilled water will be green. So you can just visualize how these contents would appear in a test tube. The tubes were illuminated through a thin glass tank filled with water, as shown. You have studied this set of apparatus in photosynthesis. You irradiate a suspension of chloroplast, which actually are there in DCPIP with this lamp. You keep the light intensity constant by keeping it at a constant distance and using the same watt of bulbs or the same number of bulbs. You keep a thin tank of water, which actually helps in dissipating the heat. So all the heat is absorbed from the light in this water, and only the light energy reach this tube, so the temperature is controlled. You keep the content of this tube covered in foil so that external light source will not end up initiating the reaction, and you can control when the reaction begins. So this is the tube 1 containing chloroplast suspension and DCPIP. This is the ruler which was used to measure 20 centimeter exact distance. The moment this foil is removed, a timer is started. And the time is taken for the chloroplast suspension and DCPIP to change its color, or for the DCPIP to lose its color. Because as the light will reach out here, the DCPIP will start to lose color. So the content of the tube from blue will start to become green. Why? Because all the blue color of the DCPIP has been discharged, and the colors which is left, the color which is left behind in the test tube will be green, which is because of chloroplast. So this is what's mentioned in the table as well. The foil was removed from tube 1, 2, 3, but left on tube 4, which means tube 4 is actually telling you what happens in the absence of light energy. A timer will start immediately after 10 minutes. The color of each tube was observed and recorded. Table 1.2 shows the results of the student results. So in this, they are not using the time taken for the color to be lost. Rather, they are keeping the time constant, and they're just seeing how much quantity, whether the color had changed or not in 10 minutes. So tube 1, 2, 3, and 4 are there. Chloroplast suspension, DCPIP, foil remove, remove, remove. The first two turned green because the DCPIP lost its color. In the third, since it was blue to begin with, it stayed blue. It cannot become green because the chloroplasts are not there. In the last, the chloroplast, DCPIP medium both are there. The medium, not the medium. DCPIP and chloroplast both are there. Since it's green, since the DCPIP is blue in color, so this chloroplast suspension will appear blue. And since foil was not removed, the contents remained blue. State why the results in table 1.2 are qualitative. A qualitative means that there is no reference to number or quantity that can be counted. So that's the qualitative data. Explain why tubes 2, 3, and 4 were included. Tube 2, 3, 4, each of these are controls. So you can explain why each control was there. For example, in tube 2, chloroplast and distilled water was there, but DCPIP was not there. In the next, the DCPIP and extraction medium was there, so the chloroplast was not there. In the last, chloroplast suspension, DCPIP all were there. Chloroplast suspension, DCPIP both were there, but the light energy was not there. So you can see one variable was missed out in each. So all three of them, they behave as controls. State the function of the thin tank. Already mentioned, it helps in dissipating the heat, and it is used as a heat trap. So dissipating the heat is the main concept there. A student then modified the investigation to test the hypothesis as the light intensity increases, the rate of light dependent stage of photosynthesis will increase. Identify the independent and the dependent variable. Again, we'll go for cause and effect. The cause is light intensity, and the dependent variable here is not the light dependent stage, rather the rate of color change. Because you are measuring the rate of color change and then relating it with the light dependent stage. So you cannot mention the light dependent stage being the dependent variable. The dependent variable will be rate of color change. Using the apparatus shown in figure 1.3, describe the method that the student could use. So again, you will be mentioning your variable, you will be mentioning your procedure, you will be mentioning your risks and the safety, and how this kind of experiment can be carried out. So you will vary light intensity by keeping the 100-watt lamps at different distances. Sorry, not 100, 10-watt lamps at different distances. You can measure 20, you can keep 30-watt, but keep the light intensity wattage constant, and you will keep them at different distances: 10 centimeter, 20, 30 centimeter, 40 centimeter, 50 centimeter. This allows the independent variable to be changed. Start the timer as soon as the lamp is switched on. Note down the time taken for the DCPIP to lose its color and the contents of the test tube to appear green. Repeat the experiment at the other distances measured with the meter rule. Volume of DCPIP, chloroplast suspension must be kept constant. Concentration of DCPIP and the chloroplast suspension should be kept constant as well. Fresh samples are taken for each reading. So we have discussed variable, we have discussed the procedure, we have mentioned how certain variables have to be standardized and how different variables can be changed. Reading of every distance must be taken 3 times using fresh samples of equal volume and concentration. Mean should be calculated to remove the anomalous reading. Avoid touching electrical apparatus with wet hands because they can give an electric shock. Use gloves as DCPIP may be written into the skin. So this pretty much covers up everything that you need to discuss, and that should fetch you 7 marks. The next one. Light intensity I can be calculated using a formula. The formula is provided to you. They ask you to calculate light intensity. You know your distance provided in the figure of 1.4, figure 1.3. If you go back to figure 1.3, the distance provided to you was 20. So if you go back there, the distance was 20 centimeter. So we'll use this value of 20 centimeter, and we'll substitute this in this formula. So 1 divided by 20 squared, we will get the answer, and the answer will be taken, and the answer can be given here, and the answer will be in centimeter per squared because the reading was in centimeter and when squared and then taken up, so it becomes -2. So centimeter minus squared will be the unit here, and the value of answer can be mentioned. The student prepared two tubes with the same contents as tube 1 in table 1.1 from the original investigation. One tube was exposed to high light intensity, the other tube was exposed to low light intensity. A colorimeters were used to measure the absorption values of samples taken from these tubes at 1 minute intervals over a period of 12 minutes. So the absorption value was taken. This was the maximum observation of the absorption value at 0 minute, then at 1 minute, then 2, 3, 4, keeping 1 minute interval constant for 12 minutes. The student noted down the absorption value. You can see this in the graph. This is how the reaction proceeded. The student concluded that the reaction reached completion at 8 minutes. At 8 minutes mean precisely at the 8th minute. So straight by the data and the graph do not support this conclusion. You can see that there is a value of given at 7 and the value the absorption value of 8. You do not have any reading in the intermediates because the student was using the data at 1 minute interval each. So you don't have the data 7.1, 7.2, 7.0, 7 minute 10 seconds, 7 minute 20 seconds, 7 minute 30 seconds, and so on and so forth. So how can the student be very sure that it got completed at the 8 minute and not somewhere before, for example, 8 minute and for example, 7 minute and 50 seconds or 7 minute and 40 seconds, something like that. So we do not know. So that's why this may not be valid. Draw a tangent and figure 1.5 used to calculate the rate of change at 6 minute interval. So at 6 minute interval, just draw a tangent, and after drawing the tangent, calculate the slope y2 minus y1 upon x2 minus x1. Your answer will come in the range of 0.2, 0.4. On figure 1.5, sketch the curve that you would expect in the tube at low light intensity. So in the low light intensity, the graph should shift upwards towards the right. If it was asked for the higher light intensity, it would have shifted lower and should have come below this somewhere here. So since it's a low light intensity, so it should go up and it should decrease gradually, a bit slower as compared to the actual graph, and it should also plateau. It should also become constant, similar to the graph here. So the shape should be similar. The last part, the student investigated the effect of three different wheat killers had on light dependent reaction. Four tubes covered in foil were set up containing the mixture table 1. As shown in table 1.3. The volume of each component in the mixture was standardized. Table 1.3 is shown to you. The tubes are shown to you as well. So the first is a chloroplast suspension with DCPIP and distilled water. Apparently, this looks to be a control. In second, third, and fourth, a separate wheat killer was added. So there are three different wheat killers: a wheat killer X, a wheat killer Y, and a wheat killer Z. The foil was removed, the tube were illuminated as the original investigation in figure 1.3. After 10 minutes, the student used a colorimeter to measure the absorption value. So this is the dependent variable, the absorption value that is measured in the test tube. The investigation was repeated a number of times and the mean was calculated. So when the mean is being calculated, you know the data is continuous and the t-test can be applied. So t-tests were used to compare the rate of the results of the tube. The results of all the t-tests are shown in the table 1.4. So let's come to table 1.4. All the table is given for p less than 0.05, which means there is 1 in 20 chance of error. Contents of the tube: no wheat killer H, wheat killer Y, wheat killer Z, no wheat killer added. So this is the control here. So if you pitch the control against wheat killer X, the result was not significant. If you pitch it against Y, the result was significant. If you pitch it against Z, the result was significant. It means both these wheat killer Y and Z had a significant effect on the absorption value, and the effect of X on the absorption value was not significant. If you compare wheat killer X with wheat killer Y and Z, with wheat killer Y and wheat killer X compared, the difference was significant. But with wheat killer X and the wheat killer Z, the difference was not significant. The difference in the measure of the absorption value. Similarly, when wheat killer Y was compared against wheat killer Z, the result was not significant. So this is the data provided to you. So you should know how to carry on the analysis of the data provided. Unless you do that, you cannot move forward, and you should not move forward unless you know what the data tells you. Suggest a null hypothesis for the t-test used for tube 1 and tube 2. Tube 1 was this, tube 2 actually was wheat killer X. So, and you were measuring the absorption value for both. So you have to give a null hypothesis so that there is no significant difference in the absorption value of tube X with the wheat killer X and tube 1. So that will be your null hypothesis. The t-tests were used to compare the means already provided to you. State what I mean to say is they already gave to you that you are comparing means. That's why you're using t-test. State one feature of data that allows use of the t-test. So you cannot mention that the means are being compared because they already gave you in the question. You have to state one other feature. The other feature is that the data is continuous. If yet another feature is being asked, you can say that the data is a normal distribution. It's a paired data. So that's it. Last part. This is actually what made me select this question from all the questions, that why I should be discussing this question with you, because of this part. Now, this part actually tells you the student calculated there were 22 degrees of freedom in each of these t-tests. An equal number of replicates for each tube was carried out. State the number of replicates of each tube that were carried out. So you need to find out the n. How is the n calculated? We know the degree of freedom is always n minus 1 plus n minus 1. Degree of freedom provided to you is 22. So you made 22 here is equals to 2n minus 2. So we just opened up this bracket. So this is 2n minus 2 here. So what we'll do, we'll bring 2 on this side of the equation. So becomes 22 plus 2. And you have 2n on the other hand. So 22 plus 2 gives you 24, and it's equals to, you have 2n. Just simplified it for n. So n becomes 24 divided by 2, and the answer comes out to be 12. The critical value for t at p is less than 0.05 investigation was 2.07. State what the results in table 1.4 tell you about the student's calculated value of t when compared the effect between wheat killer x and wheat killer y. Wheat killer x and wheat killer y. Wheat killer x and wheat killer y, the difference is significant. So the t value must be greater than the critical value. That's why it's significant. So this will be your answer. T value is greater than the critical value, 2.07, and that will be enough for your answer. So this was a tricky question. I hope this video was helpful for you. Make sure that you attend this question you're all by yourself and see where you get stuck. And I hope you will sail through well. That's it from my side. Thank you so much.